I'm Kainton the Genius, and today we are going to continue with Module 5 on Data Science and Machine Learning in Python and R for August and September 2019. And Module 5 is Linear Regression. If you look at the course schedule or the course content, you find out that this is Module 5. It says Approach to Simple Linear Regression. That is what we are going to be doing today. So you can also have access to this course outline and you'll be able to follow it. And we're going to be using Jupyter Notebook. Again, we are going to be using also this writing part here. And then we are going to mainly be using Jupyter Notebook to be able to write the programs or the scripts in Python. So without further waste of time, let's get started. So this is what we are going to be covering today in simple linear regression. We'll be looking at the goal of linear regression. We'll examine the data set. We'll see how we plot this data set, how to estimate the function, questions answered by regression, and so on and so forth, and how to interpret regression outputs and so on. So let's just get started. So now this is the background of the problem. We are statistical consultants, or you're a data scientist, and you've been hired by a company to provide advice on how to improve sales on a particular product. So we have a data set consisting of the sales of 200 products in different markets. We also provided with advertising budgets for the product in each of those markets for different media, TV, radio, and newspaper. Now, what it means is that you have this data set and they are spending this much, 230.1 units on TV adverts. They want to spend 37.8 units on radio adverts, and they want to spend 69.2 units or a newspaper adverts, whatever these units are. And the sales increase is 22.1 units, okay? So you need to advise them, how do they vary this figure? How do they increase or modify these figures to get maximum sales? So the first thing I'm going to do, I'm going to display this data set right now so that you see how it is. Now, as we are doing it, I'm also going to be explaining to you how to use Python to work with data sets. So I'm going to start a new notebook, a new Python 3 notebook. So this data set, you can also find it if you want below. And now the first thing we want to do is to import Pandas. So I can also give it a name. I click on title 8 and I'm going to call it Module 5, Linear Regression. All right, so here I'm going to put a comment here. Also Module 5, Linear Regression. So comments are actually ignored by the compiler. All right, so now we have set up our notebook. Now we want to import this data. Before we can import this data, we need to import a module. And that module is called Pandas. So I'm going to import Pandas. Pandas is used to work with data set, and a data set in Pandas is called a data frame. Now when we say import Pandas, we also want to shorten the name to PD. Now this is optional. If you shorten the name, that is fine. If not, you can also leave it that way. All right, so the advertising data set is in my local drive, and I'm going to import it by saying read pd.read_csv, and I'm going to specify the location of this file in my computer. So it's in the data orders and advertising.csv. Hopefully this is the correct one. So when I import it, I need to assign it to some variable. So let me call this variable ads data. So let me assign it to a variable ads data. So ads data now becomes a data frame. Okay, so it seems it reads correctly. So to view ads data, now I want to view only the first 5 rows. So I can say ads data. Meanwhile, if you just type ads data, you could see everything like this, and run and click on run, you can see everything. Okay, but now we just want to view the first 5 rows, so you can just say ads data.head and you'll display only the first 5 rows. So this is the data set we are going to be working with. Now we have this strange column called unnamed 0. So to remove it, you simply say, I think I could remember, you say adds data, and then you select the columns you want to keep. So we want to keep columns TV, we want to keep radio, and we want to keep newspaper. We need to enclose in quotes, newspaper, and we also want to keep sales. So now we simply override the original ads data. So we assign it to the original ads data. So if I run this code, it's going to only extract these very columns I specified. So I'm going to run it, and that is fine. So if I say ads data.head, you'll see that that strange column unnamed 0 has gone away. This is fine. So let's see. So this is the data set we are going to be working with. If you want to view the summary of this data set, you can actually say describe. I think that is describe adds data. I think there is a syntax. So describe adds data, or is it adds data dot describe? So this should be the syntax, and if you run it, it gives you the description, like the count, the mean, the standard deviation, the minimum item there, or the maximum value there for each of the rows selected. So here we have 200 items. All right, so let's go back to the presentation. Let's see. So this is a data set. We know about our data set. Now the goal is that we know that the client cannot continue increasing sales indefinitely. He needs to increase the budget on adverts on TV, on the adverts placed on TV, radio, and newspaper. And they can control this expenditure for these three media individually. So if we determine that there is association between advertising and sales, then we can instruct our client to adjust advertising budget, thereby indirectly increasing sales. So the first thing we need to do, we need to check, is there a relationship between budgets for this advertising media and sales? Because we can't just assume there is a relationship. We need to determine, is there a relationship between these two items? And that is the goal of one of the goals of linear regression. Now, we've loaded the data. Now there's another way to load the data is this, right? I've also done this. I've removed unnecessary column from the data set, as you can see. So now the advertising budgets are input variables, while sales is the output variable. So what we are saying is that we have radio, TV, radio, and newspaper. These are three input variables, and the output variable is sales, right? So the input variables are typically denoted as X, while with subscript to distinguish them. So X might actually be more than 1. So we can have a function of X1, X2, X3, and so on. In this case, we have X1, X1, X3, where X1 corresponds to TV, X2 corresponds to radio. Let me increase the font here. X2 corresponds to radio, and X3 corresponds to newspaper budget. The inputs can go by different names. We can call them, this X1 to X3 are called predictors. They're also independent variables or features, or sometimes just variables. I prefer to call them features. The output variable here in this case is sales, is called dependent variable or the response variable, and is typically denoted by Y. So what we are going to do now, we are going to extract these variables TV, radio, and newspaper into one-dimensional data set. X1 for TV, X2 for radio, X3 for newspaper, and then Y for sales. So to do that, you simply say X1 is equal to adds data, and you specify TV. So here, if I run it, it will work. And then if I check what X1 is, maybe I can just say print X1. You'll see that X1 only contains values for TV, which is 230, 44, 70, 17.2, and so on. All right, but that is not, we're not trying to do that. So let's just take out this. Let's extract x2. X2 to be adds data, and that should be for radio. X3 adds data, and it will be newspaper. Okay, so and we also extract y we extract y, that is for sales. So we have adds data sales. Okay, so if I run, that'll be fine. So we have extracted all the variables from the data frame into x, y, and x1, x2, x3 variables. Okay, so now one thing we can do is to plot these data sets to see how, by visually examining the graph of this data set, we may be able to see if there is some relationship between them, right? So that is what we want to do at this time. Now, how to plot is covered in a different lesson. So at this point, I'm not going to be explaining how to plot. I'm just going to write it without explaining it. So I'm going to say, of course, it's very easy. It's simply to import matplotlib. Matplotlib is used for plotting. So we first import matplotlib.pyplot, shorten it as plt. Okay, so now I like putting the import in a different cell. So if you simply say plot plt.plot and just say plot x1 against y, it's as simple as that. So if you say plot x1 against y, you have this. So now we need something like maybe a scatter plot. So instead of saying dot plot, you can just say dot scatter. So if you say dot scatter, it will give you a scatter plot. So now in this case, we have x1 against y. So you can see there is some kind of linear relationship such that when y is increasing, x is increasing as well. All right. So when we say x1 against y, I think that should be kind of wrong. It should be y against x1. So it should be y against x1. So in that way, the y values, I think, let's see. So let's go back up. So y values, y ranges, the sales ranges from 27 to 200. Okay, x1 is TV. It ranges from 147 to 296. Okay, so let's get back to the plot. So okay, so this is just a plot. So if I invert it, y against x1, let's see how it looks like. So it's basically about the same thing. So like a linear relationship. So in this case, what happened here is x is on the y-axis, which is wrong. So it's x1 by y. So that's the syntax for plotting in Python. All right, so let's plot the other two. So the same way you can say plt.scatter, you say x2 by y, and plt.scatter x3 by y, okay? And then finally, you say plt.show so that the tree can appear. So if I run this at this point, you say the tree appeared on the same curve, but that is not what we want. We want the three of them to appear on different curves. So to do that, you simply use a subplot. You can say plt.subplot. So it should be 1 by 3. And in plot 1, that is where we are going to plot the first one. So let me just copy this. For plot 2, I'm going to plot it at point 2. And for plot 3, I'm going to plot it at position 3. Okay. So at this point, if I run, you can see that the tree appeared in the same place But we can now improve the appearance by using plt.figure and then say fig size equals 10 and 5. Again, I want to give them different colors. So for the first one, I want to say color is equal to red. For the second one, I want to use color is equal to green. Okay. So I'm going to run again and let's see. Okay, so this is better, right? So this is how the plot looks like. So there seems to be some relationship between the first case between TV and sales. So if we're increasing the budget for TV adverts, sales tend to be increasing. But we can't be sure until we perform linear regression to determine the equation of the regression line. Let's get back to our presentation to continue. So now this is where we are. More generally, suppose we observe a quantitative response y and p different predictors. In this case, p is equal to 3. We assume that there is some relationship between y and x. X is equal to x1, x2 to xp, which can be written in the form y is equal to fx plus e. So we'll always assume that we have observed a set of n data points, and these observations are called training data because we will use this observation to train or teach our model how to estimate f. Again, I'm going to just explain briefly what we are doing. So one thing you need to keep in mind is that if you are given this data set right from the start, up front, you are given a data set that has both the predictors and the response variable. That is more like you are having a data set that is complete. You are not doing any prediction with that data set. You are just trying to understand how the data set looks like, and you are going to use it to train your model to be able to estimate when there is new predictor variables or new x variables, what will y be. That is what this data set is used for. And that's why it is called the training data set. So I'm going to kind of write it here. Let me pick some kind of pen. So I'm going to use a pen. So this should be called training data set. Training data set. So you use it to train, to teach the model. So that is where learning, the model has to learn. And that's where learning in machine learning comes in. So this data set you have, you are going to use it to teach your model so that after you teach your model, when your model now sees a new independent variable on a new predictor variable, it will predict. This is going to be what the sales will be based on these variables I have. So let's proceed. So let xij represent the value of the jth predictor for observation. Okay, now I'm not going to spend time reading this because this is very much theoretical. So meanwhile, our goal is to apply statistical or machine learning method to the training data set in order to estimate the unknown function. So what we are saying is that there is some relationship or function that holds x and y. So if we take them individually, so let's say we are trying to determine the relationship between radio and sales, and we have that radio is x1. So we are saying that sales is y. So we are saying that function of x1 is equal to y. So what is this function? That is what we are going to estimate. Now in linear regression, we have to make an initial assumption. And that initial assumption is that the relationship between these two variable sets, between the predictor and the response, is linear. And that is where the linear regression comes into play. We make an assumption initially that there's a linear relationship between the predictor and the response. So the question is going to be, is there a relationship? That is what we are going to answer. How strong is this relationship? We are going to answer it later on also. Spend time to read and understand the explanation in this concept. and which media contributes to sales. So when we move on to multiple linear regression, we see if there is interaction between TV, radio, and newspaper, and which one actually contributes the most, right? So this will be talking about multiple linear regression. How accurately can we estimate the effect of each medium on sales? We'll be talking about p-value, p-value. If I'm not mistaken, no, this is not p-value. So here we'll be talking about r squared. So again, I'm going to just, I cannot undo this. So r squared and adjusted r squared. So permit me to go back. Is there a relationship? Here we are talking about, so whether there's a relationship that exists, we are talking about regression. So we are talking about least squared regression. How strong is the relationship? Now we are talking about the coefficients, the regression coefficients, and maybe the r squared, maybe also. So we also, how accurately, here we now have the p-value, how accurately we are talking about the p-value. So my pointer is giving me some problem. Okay, so fine. So here we are talking about the p-value. Where do we have the t-statistic? Is the relationship linear? Okay, so is there any synergy among the advertising media? So here we're also talking about linearity. So many of these questions we are going to answer in other topics in regression. So for now we are talking about simple linear regression, where we are going to determine whether a relationship exists and how strong is this relationship. All right, so simple linear regression leaves up to its name is a straightforward approach for predicting the quantitative response y on the basis of a single predictor variable. So here we are going to take each of these advertising budgets individually. So we are not going to take them as a whole. So we are going to consider what effect does TV have on sales, what effect does radio has on sales, and what effect does newspaper has on sales, while ignoring the other one. So each one we consider, we are going to ignore the other ones, all right? And that's why here we have simple linear regression. Later on, we talk about polynomial regression or logistic regression or multiple linear regression. So it assumes, simple linear regression assumes there is approximately a linear relationship between x and y. So take notes, we are assuming a linear relationship. So whatever function we are going to come up with is going to be linear. The x always should have the order of 1, or the function will have the order of 1. And this is what the relationship would look like. Y is equal to beta 0 plus beta x. It says you might read it as y is approximately modeled as. The reason is because whatever estimate you get, whatever function you find out is an approximation, is not the exact true value of the relationship. It's an approximation. We are hoping that it's close to the true value of the relationship between the two variables in question, the independent variable or the predictor variable and the response variable, which is also the dependent variable. We'll sometimes describe by saying that we are regressing y on x. So in factor analysis, you always see something like regress y on x or regress this variable on this variable. So if we use our data set, we are saying that sales is approximately equal to beta 0 plus beta 1 times the advert on TV. So in this case, we are considering TV, which is x1, right? So let's move on. So equation 3.1, which is the previous one, it says beta 1 and beta 2 are unknown. They are constants that represent the intercepts and the slope. So in high school, we used to talk about the equation of a line, and the equation of a line in high school, we used to write it as y is equal to mx plus c. So basically, if we have an equation, normally we use a graph book, but not now. So if we have some equation and we plot it on a graph, right? And it gives us, I'm going to take another color at this point. Let me see if I can get the color. In color, let me use, let's say blue. So we plot it and it gives us a line like this. So we are going to measure here, which is C, and we are going to also take the slope of this line. The slope of this line is going to be, of course, you know that is y1 minus y2 over x1 minus x2, if I'm not mistaken. So this is the m. Okay, so this is slope. M is the slope and C is the intercept. But in linear regression, we have this corresponds to C and this corresponds to M. So it's basically the same thing. We plot this data set and find the slope of this graph and also find the intercept on the y-axis. All right, so note that the intercept on the y-axis is prediction of x, of value of y when x is 0. So basically, we are saying, assuming we don't spend anything on adverts. Let's say, assuming we don't spend anything on TV. Sorry, let's get back to... Okay, I think I mixed up a few things. Okay, so this is where they are saying, assuming we don't spend anything on TV, it means that sales will be beta 0. Of course, we'll have sales, but it will not depend on TV. And that in that case, the coefficient of regression for TV is going to be 0. And that is the where we have the intercept to be B0 on the y-axis. All right. So the focus on linear regression is to estimate the regression coefficients. I'm going to write it down. I'm going to take pen. Estimate, I think it's estimates the regression coefficients beta 1 and beta 0. So this is what we are trying to do. Now, in case of several parameters, we can have several betas, beta 1, beta 2, beta 3, and so on. But for now, we are taking the simple one. And eventually, we will use Python to solve this problem to find these coefficients in Python. So these are the steps I'll recommend you try to copy out these steps and try to go through it. Of course, we are going to follow this step right now to determine the coefficient of regression and also determine the function that relates y and x using Python. All right, so one thing I recommend is also something called to do a pairwise plot, right? So a pairwise plot is a way to plot all the graphs, all the whole data set in a grid form, in a plot that is on a grid form. I think the easiest way to do it is to just do this pairwise plot so that you actually see how it is. So pairwise plotting is very important in data analysis for you to have an initial visualization of what your data looks like. All right, so I'm going to do a pairwise plot at this time. So the module that we can use is Seaborn. There are two ways we can use Seaborn to do pairwise plotting. So I'm going to just say import Seaborn. Seaborn is another model for visualization as SNS. After that, you simply say sns.pairplot and simply specify your data frame. Our data frame is adds data. So at this point, if I run it, it's going to give me something called a pair plot or a pairwise plot. So it takes a couple of minutes, but it's going to display. All right, so give a second. So this is what is called a pairwise plot. So here you can see interactions between different variables. So here you can see TV against, let's shift this one a bit down so that we'll be able to, okay, so let me extend this. So for some reason, I'm going to just maximize. Okay, so we actually have TV against TV, TV against radio, TV against newspaper. So you can actually look at all the interaction between all your variables to see on a bird's eye view how they interact. And pairwise plot can always help you. So if you see there's no relationship, you may even actually give up doing linear regression because it's not going to make sense. But for now, it seems there are some trends in the data set. We can also do a pairwise plot using Pandas. So we import Pandas, pandas.plotting as pp, and we simply say plots is equal to pp.scatter matrix. And the scatter matrix, we are going to use the same data set, adds data, and specify. This time, let's say let's just do the same thing we did. Let's not restrict the data set. So I'm going to run. Okay, so we have the same thing that we did originally, right? So you can see it gives us exactly the same thing. So this is what is called a pairwise plotting. So have it under your belt. As a data scientist, you need to use pairwise plotting from time to time. Anyway, let's continue from where we stopped. Let's determine now the coefficients of linear regression, beta 0 and beta 1 in Python. That is the next thing we are going to do. We want to determine beta 0 and beta 1. So to do that, we have a module in Python called sklearn.linear-model. This module contains linear regression, so I'm going to say from sklearn.linear linear_model. From here, import linear regression. All right, so if I run this, hopefully it's okay. I've imported linear regression. So what we can do also is to reshape. Now this reshape, which is this line here, I'm sure you don't have to worry about it. It's something about feature extraction or pre-processing that we are going to talk a bit later. But it's something you'll need to do. X1 is equal to X1 dot values dot reshape -1 to +1. And the next thing you want to do is to say, now you create a linear regression object. So let's call this linear regression object lin obj, lin object, linear regression object, or linear regression variable, anything you want to name it, is equal to linear regression. Okay, so I'm going to run as well. Okay, good. So you now need to use this linear regression object to fit the data set, right? So we are going to use it to fit the data set. So I'm going to shift this. To do that, you simply say linear regression variable dot fit, and we are fitting for TV against cells, so X1 against Y. So we are performing linear regression for TV and cells to see how TV relates to cells. That is what we actually want to do right now. So I'm going to say run. All right, so now we've performed linear regression. How do we now know the intercept and the slope? How do we know the linear regression object? So now I'm going to put a comment, find, okay, I cannot write beta here, so let me just print lin var.quef. I'm going to run this, and again I'm going to say print lin var.what? Intercept. All right, so this we have the coefficient and the intercept, and you already know that the coefficients is the same as beta 1 and the intercept is the same as beta 0. At this point, I'm going to use the blackboard or the whiteboard to now write the equation relating the sales and the TV, the ads placed on TV. So I'm going to simply replace, at this point, I'm going to write, here we have beta 0 is equal to what? Is an intersect, which is 7.03, and beta 1 is equal to 0.047. 0.4048. Okay. Now to write the regression equation, which is y is equal to f of x1, which is equal to 7.03 plus 0.048 x1. In effect, we are saying that sales relates to TV adverts in this way, 7.03 plus 0.048 TV. Let's put it this way. We are not done yet. But we've come a long way. At least we've determined the regression coefficient, but we see there are other questions that we raised. For instance, how accurate is this model? How strong is this relationship? And can we rely on it? That is another question. So that is the next thing we are going to ask ourselves. And there are some parameters that is normally used. So let's move on to the next slide. Now we need to get additional data, regression data to use. Additional regression data can be gotten using another module that is more powerful than sklearn.linear model that gives us linear regression. So the procedure we are going to be using here, we are going to be using statsmodel.api is another module. So this model is going to help us perform linear regression and is going to give us several other data that is very, very important in regression. For instance, the R-squared, adjusted R-squared, the p-value, the F statistic, the T statistic, and so on, and many other things. So let's quickly perform this linear regression again. This time we are going to be using statsmodel. So I'm going to write a comment, linear regression using models.api. And the first thing we want to do is to import statsmodel.api as SM. Okay, so I'm going to run stats models. So actually stats models and not stats model. All right, so we are still using the same data, and we are going to say x1 is equal to sm.add constant. So here we are saying that add constant is a way to add the independent variable. So stats model calls the values of the independent variable the constants. So here we have x1. All right. And finally, we also do the same thing. This time, let's call it linear variable 2, because we have already used linvar for linear regression in sklearn. Now we are going to say sm.ols. OLS means ordinary least squared. So the method being used here is ordinary least squared regression line. So I'm going to say y against x1. This time we are trying to regress y on x. So try to say it several times. We are trying to regress y on x. Okay, so dot fits. Okay, so at this point we perform the regression, and this object linvar2 contains a whole lot of variables that we need. Right? So to prove that, to show you what is in there, we are going to say linvar2.summary. Let's run it and see. So now we see a whole lot of things that explains everything about this relationship between these variables for us. And we are going to be talking about this a little later. For instance, we have the standard error, we have the t-statistic, we have the p-values, and we have the r-squared, adjusted r-squared, f-statistic, and so on. A whole lot of things that we can use. We have residuals, 198. All right, so now let's talk about some of these things. And for us to talk about it, we need to still go back to our presentation. Let's continue. The regression results provide details of the least squared model for the regression of a number of units sold on TV advertising budgets for the advertising data. So what we are saying is that we have the coefficients beta 0 equal to 0 and beta 1 equal to 0 are very large relative to their standard errors, so that t-statistic is also large, and the probabilities of seeing such values if H0 is true are virtually 0. I think I should not. Okay, so something is actually not right here. So I will say we can skip this because we are talking about inference from linear regression. Okay, so I'm going to skip this because I'm going to talk about, let's talk about least square regression line first. Then from there we now talk about a few other things. So let's try to fit a least squared regression line. And then after fitting a least squared regression line, then we try to interpret the regression results. Okay, so to do that, the first thing I'd like to do, I'm going to plot. First, I'm going to plot. I'm going to write y is equal to. Now we have beta 0 and beta 1. So let's write the function for beta 0 and beta 1. So let me open the whiteboard. All right, so this is where we are. Let me shift this out a little. So y is equal to write this equation, I'm going to say 7.03, right, plus 0.048 x times x1. All right, so this is what y is. All right, so I'm going to run. Okay, but we have a problem. Now I'm going to go back at this point. I don't want to overwrite y from here, so I'm going to run this, and I have y assigned. So I'm going to call this y1. Okay. So whatever value we have for y1 is estimates of what value y should be. So meaning that literally we can go to the data set and take values from TV, fix it into the equation, and calculate y. So what we are saying is that, let me give you an example. Let's assume that we have the value for TV 230, and we want to calculate the sales using our model, right? So let's calculate sales using our model, right? So we are calculating sales to be equal to, using our model, to be 7.03 plus 0.048 times 230.1. And that is going to give us, at this point, I'm going to do this in Python. So after, I'm going to actually remove it as well. So we have that sales is equal to 7.03 plus 0.048 times 230.1. Okay, I'm actually not going to call it sales. Let's calculate this and see what it gives us. it gives us 18.0748. If we check it against the value of sales here, let's check it. We have 22.1, right? We have sales to be 22.1. So we have an error of 22.1 minus 18.0748, right? 22.1. So this is the error, or the residual. Is also called residual error, or whatever. Okay, so this is the error incurred by our model. Our model is not accurate. It gives an approximation. At least it gives something close. 18 is not too far from 22. Okay. All right. So we now want to fit a regression line through the model. So the first thing, if I plot the original data for plt.scatter, and I plot the original data x, 1, and y. Remember that. Okay, let's just do it. Okay, fine. Now I'm going to also plot a line. This time plt dot plot, and this time I'm going to plot x1. This time against y1, and in the same plot I'm going to say plt dot show. Now I'm fitting a linear regression line into against this very plot. Okay, I'm going to say color is equal to red, and line width is equal to, let's say 8. Okay, I don't know if 8 is too much. So if I run it now, it's too much. So let's just reduce it to 3. All right, so you can see that a least square regression line has been fitted through the data set. Now I'm going to also try to do something. I would like to say, just give it a second. I think I did something like that here. So this fig size, I'm going to just take it, plt.figure. I want to make the figure to be a bit large. So control, okay. So fig size, let's say 10. If I use 10.5, let's see. Good. Okay. How about if I increase to 15? To 15.5. Let's try 15. So for some reason this thing does not work. 15.5. I don't know. Okay, good. Or if I increase this to 8. All right, so what we are trying to do is that we are saying that the data, the least square regression line that we are fitting is giving some error. Now, if we check this point to this point, is called the error. There's an error here called residual, right? Okay, so least squared means that we are trying to minimize the error between our least square regression line and the data set, meaning that we want this regression line to pass through, to touch the data sets, or pass through in between the data sets as much as possible. So this is how we fit a least square regression line. Let's see what we have next. So now this is the regression results, and this is now, we are now going into bits of statistics. Since another module covers statistics in details, then I'm going to stop here and then allow you to practice this, and then we move on to p-value statistics, hypothesis testing, how all this applied, and more especially we'll spend some time interpreting these beautiful results we have here. That is what we are going to be doing in the next class. So I hope you understand everything we did. So we have still a long way to go, a standard error, confidence interval, and so on, all the way to multiple linear regression. But for now, let's keep it simple so that you can take some time to practice this and get used to it.